In this video, we're going to take a look at left-handed and right-handed molecules. Left hand, right hand. Now, the idea that molecules could be left-handed or right-handed is kind of weird, and it's hard to wrap our heads around that. And so I'm going to use a couple of metaphors, I'm going to use a couple of models here to try to describe this. But to begin, we have a left hand and we have a right hand. And we recognize that our hands, we think they are the same, but they are not superimposable. And that is to say, they're like mirror images of each other. If I were to have a mirror right here, we'd say, well, here's one, here's the other. They'd say, hello, how are you? But they're not superimposable. That is to say, you can't put one right over the other and have them cover each other perfectly. Okay, a little strange. Now, I have a molecule model here. And in this model here, you can see I have different colored balls here. I've got blue, and I've got green, and I have red. And I've got the same thing here. And if I line this up here correctly, like this, we can see that the greens line up with the blues, line up with the reds like this. So they look like they're mirror images of each other. And the question is, are they the same thing? Aren't they just the same molecules? And so let's just say one of these molecules was something tasty here, and it's going to land on your tongue, and you're going to taste it. So if we have, say, your tongue here, like this, okay, here's your tongue, and then on your tongue you have taste receptors. You have molecules on your tongue that connect onto other molecules and send a signal to your brain, and you're like, that tastes good. So here we have a taste receptor on the brain, and that taste receptor lines up like this, where we have, say, green right here, okay, and then we have a red over here, like this. There's red, okay, and then we're going to put blue up here on the top, okay, so blue right there on the top. Okay, so that's our taste receptor. And if a molecule comes along and it lands right there on that taste receptor, it sends a signal to the brain and says that's yummy. Okay, so it's got to line up like that. Now, if it lines up like this, okay, where, well, wait a minute, this is white and this one here is red, okay, that's not going to work. Okay, so this molecule here lands on the taste receptor, and we take the mirror image of that molecule. We take that mirror image and we bring it along like this. And we go, okay, so here's blue, and here's green, and then, oh, there's white there. Okay, well let's rotate that so that way we get the red there, and then the green, but well, now it doesn't line up there. And so even though these two molecules are mirror images of each other, they're mirror images of each other, they're not the same. And so we say that these molecules are chiral. Okay, and chiral means that you have a carbon atom in the center here like this, and you have four unique things coming off of it. So this is how you can identify a molecule that could potentially be chiral. Now, a couple of examples of this would be caraway and spearmint. Caraway and spearmint, we have two molecules here, and they look very much the same. But we have a carbon atom here and here that have four unique things coming off of it. And that means that these two molecules are different. They look very similar, but they are different. And so when these land on your tongue, one tastes like caraway, the other tastes like spearmint. Now, in a molecule, if we were to draw out a molecule and try to identify what is a chiral center, well, you might have, say, a carbon atom in the center like this. So we know carbon likes to form four covalent bonds. And then if we have four unique things coming off of it. So like, let's just say we have a carbon here, carbon like this, and then a hydrogen, and then a bromine like this. This carbon atom right here has four unique things coming off of it. So there's a methyl group here, and there's an ethyl group. And you might say, oh, wait a minute, that's just a carbon. Isn't that just like that carbon there? No, this carbon is different than that carbon there, because there's two carbons here. Okay, so there's four unique things coming off of that carbon atom that makes it chiral. So then what if we take a look at, say, an oxygen atom? If we have an oxygen atoms like to form two covalent bonds, and then they have a couple of lone pairs like this. So the question is, could an oxygen atom be a chiral center? In other words, could that be the source then of a mirror image or two different molecules that look similar but are different? And the answer is no. And that's because an oxygen atom cannot have four unique things attached to it. You might have, say, a carbon here, and then a carbon like that, and that's one thing, there's two things, and then those lone pairs, no. So there's really just three things, three unique things. We have like a methyl, we have an ethyl, and then we have lone pairs. So an oxygen atom cannot be chiral, but carbons definitely can. Now, this gets a little bit tricky when we take a look at ring structures. So if I have a cyclohexane like this, cyclohexane like this here, okay, and then coming off of that, I'm going to put a hydrogen, and I'm going to put a chlorine like this. Okay, so we're looking for a carbon atom that has four unique things attached to it. And right here, we would have a carbon atom, okay? And this carbon atom has a hydrogen, and it has a chlorine, so that's two unique things. And then attached here, we have a carbon and a carbon, all right? And so there's four things, but is this carbon any different than this one? And the answer is no, because as we go this way, it's the same as if we went this way. It looks the same. And so this here would not be a chiral center. But what if we made something a little bit different here? Like what if we put a double bond here, like this? Now, this carbon atom is different than this one. So as we go around this way, this carbon atom has a double bond attached, this one does not. And so then this does become a chiral center. This would be different. Another example might be if we had, say, coming off of here, maybe a chlorine atom, and then down here we didn't. And so going this way, this carbon atom would be different than this one. What it's attached to would be different. And so again, this would make this one here, this carbon atom here would be a chiral center. This molecule here is Albuterol, and you don't need to memorize this or anything like that, but you might recognize the name Albuterol. Now, Albuterol is a molecule that is very familiar to asthmatics, and as a parent, I had a child who is asthmatic, and we had to give our child Albuterol before he'd go to bed, so that way he'd wake up in the morning. And the Albuterol is a bronchodilator. It helps open up the lung passages so that way he could breathe. Now, Albuterol is the right-handed version of the molecule. So here's Albuterol. Albuterol means that this right here is our chiral center. We have a carbon atom right here, and we have four unique things coming off of it. Coming off this way, we have a phenol. You can see the benzene ring and the OH there. There's a phenol, okay? You have a hydrogen, you have a hydroxyl, and then you have this chain coming off in the other direction like this. Now, the way that I have it drawn, I have kind of like a wedge triangle here showing that this hydroxyl group is coming out of the board a little bit. And then this kind of a dashed line here with the hydrogen is trying to show that it's going into the board. What I'm trying to do is make this look three-dimensional on a two-dimensional surface. Now, albuterol comes in the form of a salt. And if we remember back to a previous video, oftentimes medications are turned into salts to make them soluble in the plasma. So albuterol comes as a hydrochloric acid salt. So if we take HCl like this, the hydrogen becomes a positive ion, chlorine becomes a chloride or a negative ion. And so that hydrogen ion is attracted up here, like this, and then the chloride ion is attracted to the whole molecule. So this becomes albuterol hydrochloride, or R right-handed albuterol hydrochloride. Okay, now here's the thing about albuterol. Albuterol is a chiral compound, and that is we have that stereo center here, or a chiral center, and so we can then actually make another version of this. And if we were to like flip-flop this like this, and then put our hydroxyl group down here and our hydrogen like that, it's a different molecule. And this becomes L albuterol, left-handed albuterol. And it's like, okay, so you have a right-handed and you have a left-handed. Remember we had caraway and spearmint? They tasted different. What's the difference between left-handed and right-handed albuterol? And it turns out that one of these molecules is a bronchodilator. It helps asthmatics to breathe. The other molecule acts almost like amphetamine. And as a parent, you want your kid to go to sleep, you want them to wake up in the morning, you don't want them all antsy and crawling up the walls. And so a chemist figured out how to separate out the two different versions, the two different enantiomers of albuterol, left-handed and right-handed, and would sell just the left-handed version, and that it came in a different name that was called Xopenex. And Xopenex was more expensive because it was just the left-handed version of the molecule. And as a parent, you're like, shut up and take my money because you want your kid to sleep through the night. Now that we've gone over what is a chiral center, if I were to give you a molecule such as this, and then ask you, can you identify, is this molecule chiral or not? You should be able to look at it and see, is there a carbon atom that has 4 unique things attached to it? And if it does, then it is a chiral molecule.